I need to clarify something here. I keep on calling these common emitter configurations. They're not common emitter. They're emitter followers. The input is coming into the base, and the output is coming out the emitter. That's the emitter follower amplifying configuration. Okay, so now I got that corrected. I get these corrections after I watch my videos to edit it, and then I catch myself on these things. Okay, so now that takes care of change number 1, and as I said, we're now going to go to change number 2 and see what's involved there, which we said was going to be the PNP transistor. And now I'm going to go ahead and build this part because we're now up to this area right here now. And now I'm going to do the build for it. Okay, we're removing pull down resistor 3.6K. We're removing that and replacing that now with this. Okay, the circuit is built. There's the PNP transistor. Here's the bias resistors for it. That's right here. We're going to take a voltage measurement now from ground to here to see how close we are to 11 volts, and then take a measurement across the motor and see how close we are to 6 volts. Plug the power in here, and we're going to check here first. We're going to check the voltage output of the regulator. That would be right here, and we're looking for close to 11 volts and about 10.5 volts within reason. Now across the motor, and we are at, well, 6 volts. We're 6 volts across the motor. So the circuit's working properly. So what that means is this. It means that since we have 6 volts across the motor, that means that we're getting the same value of motor current. So it means that we have proper bias going on here, that the original circuit from the beginning, circuit number 1, we had a specific voltage at the base here of this transistor here, and that voltage determined the output voltage. Then when we had a change to a higher voltage, we end up with this part of the circuit here, and we end up with 11 volts here now we had to use. That again, that means that we have proper bias here because we still have 11 volts here and 6 volts here when we added the next transistors, which was this transistor here. So now that we have all these transistors working properly and we're getting the same voltage, that means that everything is biased properly. So now we move on to the next stage of designing this here. As you can see, the input impedance is improving, getting higher. The original, we had 24 ohms input impedance. Now we're at the point of 4.7K being the lowest. So we have really increased our input impedance from the first design change. Okay, so now we're going to go to the next design change, and that's coming up next. Alright, now the reason why that we wanted higher input impedance was for one reason only. We want to drive all the current through the motor through this branch right here. Any current that comes off of this branch here to go into the base of this, we want only as signal current only. By using this 24 ohm resistor here, we would have driven current through the 24 ohm resistor, and we have had 2 branches of current for the motor, and we don't want that. That's why we have to raise the input impedance, and so that's what we did here. However, now that brings us to another situation though. Now that we have a very high input impedance with respect to before, we can now take our motor current and go into the base of this, but that's not going to work, and here's why. Because if we have a higher input impedance here, that means then a very small change in current here introduced into the base here is going to cause a great effect very quickly, and we don't want that, because under normal motor running conditions we do not want this circuit to be activated whatsoever. We want it to remain stable. And so therefore, because it's high input impedance, that comes with the cost of needing to isolate this now from the motor current so as to only come on when the motor current is needed to come into here. And that's going to be the next design step. Okay, so now we are going to feed motor current into here, but we want to feed it into there only when the motor needs more current fed to it. So we have to break this line right here, and we have to insert now another circuit that will come on only when there's a demand for more current from the motor. So this has to be a sensing circuit, or better known as, we'll call it a voltage controlled current source, which again would be another passive or another active component, and it will act as an infinite impedance when the motor is running under normal conditions. But when there is a load on the motor and there is a need for more motor current to flow into it, this signal will close a electronic switch that will allow that current now to flow according to the need for it to flow through here linearly with the motor current the voltage dropping and the current increasing. So this will be a electronic switch, a voltage controlled current switch that will switch on at a threshold voltage. And that brings us to the next design change. If I put a NPN transistor in there and I bias it in such a way that it would be in cutoff, it'll be in cutoff until the motor voltage drops to a certain value, a predetermined value, that would cause the emitter of the NPN transistor to go below the voltage of the base that was pre-biased. And when that voltage drops low enough, then this transistor will start conducting, and then current through the motor can flow through here as signal current to cause the effect that we're looking for. So now we need to design this here voltage control current switch. And now if you look at this here, this too is a common base amplifier configuration. We have the base bias right here, and we have the emitter current being this is the input now. The emitter is the input and the collector is the output. And so therefore we now have a switching application here that can be infinite impedance under normal running conditions, because it's biased and cut off, so it's actually cut off all current flow through here until the motor needs more current, and then of course when that voltage drops below there, it then comes on as a switch and sends the current through there. And the nice thing about this is this will only send the amount of current that the motor sends to it. It's not going to amplify the current, it's just going to allow the current to pass through there with respect to the amount of current that flows through the motor through there into here. Okay, so let's get this here design going now and show you how I got these values. Alright, now to solve for this arrangement here, I need to get the values of these here base bias resistors here. In order to do that, I have to solve for the amount of current that I would like to have come through this transistor here to be used as a signal current. The way I did that was I experimented. I put a resistor across R4 here, which would lower the base voltage of Q5, which is a PNP transistor. By doing that there, it would raise the voltage of Q1 up. So I put resistors across here until I got a voltage across at the output of Q1 that was almost pretty much saturated Q1, where it's at its highest output. After that was accomplished, then I took a measurement, voltage measurement across R5, so I can determine the amount of current increase that I needed to get that. Now I originally had 500 microamps flowing through here to bias this in the linear region right there. When I took that measurement and I got a current increase here, I then subtracted this 500 microamps from that, and that gave me the amount that I would need then of feedback current to cause that kind of result. It ended up to being about 750 microamps, maybe 800 microamps it ended up being whenever I put a voltage measurement across here and calculated the current increase. Now with that current being established, again I take 1/5 of that value there for the bias current for this transistor. Now what I wanted to do was to keep this in cutoff. I just simply took the voltage at the motor and subtracted one base emitter voltage drop, which is 0.7 volts. So I took the 6 volts, subtracted 0.7 volts from it, and designed it for 5.3 volts for base voltage here to be pre-biased at. And then I just used Ohm's law to get the values for the resistors. I took the 5.3 volts for the pull-down resistor and I divided that by the current that we now said would be, which is 1/5 of this, which is 50 microamps now, to give me 110K for the pull down. And then just do the same thing here. Now the base goes directly to the main supply, so I can keep a stiff base voltage here and not have it fluctuate with any change up here. And so again, Ohm's law gave me 220K ohm for the pull-up resistor, and then by putting a variable resistance in here, I can adjust that, and I can pre-adjust the sensitivity of this here by raising the base voltage or lowering it so that it would respond to the drop in 6-volt motor more readily or less readily, depending on how sensitive I make it. Okay, so now let's go ahead and build this, and then we can actually test it by putting a load on the motor and seeing if we have an increase in voltage of Q1. And that's going to be the first dynamic test to actually see if the feedback is now going to work. And that's coming up next. Okay, here we go now. Remember, this transistor is acting as a current switch, a voltage controlled current switch or current source. Voltage controlled. It has to remain out of the circuit during normal motor running conditions. It has to have an infinite impedance. When the motor demands a current to it under loaded conditions, it has to turn on. Here we go. I'm going to turn the circuit on here now. Now first of all, this wire is the input from the motor, and this is the feedback transistor Q8. This is this transistor right here now we're working with. This is the input to that transistor. Without the motor feedback, I'm going to stall the motor, and we're going to look at the voltage across this point right here. This is the voltage we're looking at, the voltage at the output of the regulator now. It's going to feed into here. I'm going to stall the motor, and the voltage remains. There's no change in voltage output, which is good. That means the regulator is working. Alright. Now I'm going to put the motor signal, or the signal wire. Now this is the feedback wire. This is the feedback from the motor. Now with the feedback connected, the voltage still remains the same. Now if the voltage is still remaining the same, that means then that this circuit is not operating. It's acting as an infinite impedance. Now I'm going to stall the motor, and the voltage rises up. I'm going to let go of the motor, and it goes back to 10.58. As I stall the motor a little bit at a time now, watch the voltage rise. I'm going to put a load in the motor now. The voltage is increasing, and back normal again. I put a stall on the motor. The motor current is going through here. This is now switching on, sends a signal to here, and this raises in voltage. Now that's the first dynamic test of this concept that it is working. This is acting as an infinite impedance until the motor has a load on it, and then it switches on, and then the circuit works as a torque converter to this point. Now that's working on that basis there, but there's still one more problem to overcome now to get current to the motor and to get power to the motor under demand. That still needs to be addressed yet, and that's the next circuit change. But this one is now proof of concept that we can get feedback current into here when it's needed, only when it's needed, and not when it's not needed. When it's not needed, the feedback current remains 0. When it's needed, it comes on, and that was the dynamic test for that part of the circuitry now. Okay, the next part's coming up now. That's going to be an enhancement to cause this motor now to receive more output power to it now that's necessary to make it run better. And that's coming up next.